Let's take a look at a few examples that deal with both impulse and momentum and talk about how we know which formula to use, why, and some of the tricks that are involved. So this question is describing the change in motion, the change in velocity of a baseball as a force acts during a time. This is all about the idea of impulse causing the change in something's momentum. And so this would be a basic formula we would use. I actually, though, like to rewrite this using sort of this idea that the initial momentum plus the impulse tells me what the final momentum is. I just think that that's a better way of thinking about what a change in something means. It means that the initial value has changed by some amount. And so, of course, momentum is m times v. So you could, again, rearrange the formulas a little bit. Please write the formulas down as, in your notes as you best think they should be. Something else I want to notice about this problem, though, is that it talks about a baseball's mass of 140 grams, and that is not our standard unit for mass. So we'll start to see a few grams in some of our problems here. There are 1,000 grams in 1 kilogram, and so we would end up dividing and getting 0.14 kilograms. Now it's a matter of pretty much just putting things in because everything is moving in one direction, and so I don't need to worry too much about the signs, the plus or minus signs of things. I have a baseball that was initially not moving. Okay, it does sort of talk about that in the problem, gives you the initial speed. And then we have a force and a time that is, again, representing the impulse, what's being added to the momentum. And then that would determine the final momentum, again, the mass of the ball times some unknown v. And so we would do some algebra and find out our speed, which is pretty fast. But actually, if this is a baseball pitcher's throw, this is closing in on 100 miles per hour. That's not impossible. All right, so now that ball is heading towards the batter, and the bat is going to exert a force of 1,150 newtons in the opposite direction. So that's a real key phrase there, opposite. When you see something like that, that has to be a warning light that that negative signs are going to have to be part of the setup here. So let's take a look at what this, how we could do this. We would start with that same idea that the momentum of the ball, which would be its mass times this velocity that we just found, is going to be affected by this new impulse, this new force times a different time. And that will determine the momentum of the ball after it's been hit. So I want you to notice a few things here. Again, that final velocity from the last part of the problem becomes our initial velocity here. We're continuing the story. Also, the fact that the force was exerted opposite to the motion, we've got a negative sign in there for that force. So that momentum is being taken away. Our time, and then again, we're going to solve for the speed. Now this one did actually ask for velocity, okay? Velocity not only includes how fast it's going, but in what direction. So my final answer, I would want to include something about it moving in the opposite direction. And how did I know that? It was because my answer came out negative, just like the force that I had put in to the problem. So I had defined what negative meant when I put that negative 1150 in there. And that helps me interpret what the negative sign means here. All right, let's take a look at a question then that involves a collision. Okay, so right away you can see a difference between problems that we've done in the past because there are two objects in the problem. There's an interaction. And again, this is where this whole collision idea is going to come to play here. The idea that we want to focus on is not impulse. Notice we're not given any information about newtons or seconds. We want to focus on the idea that the initial momentum of the whole system, both carts together, is going to equal the final momentum of the whole system, keeping in mind that momentum is m times v. This is the way I like to write my initial statement of a solution down. It's very clear as to why I'm setting up the equation the way I'm going to. Some people like to go through and put in a lot of subscripts and sort of write out something like this, and you are welcome to do so. It's really kind of a preference, but somehow you need to indicate, hey, I'm using momentum and I think it's conserved. I think it's the same before and after the collision. Let's take a look at how the numbers look when we put them in. So the blue car has a mass of 4 kilograms, but it's not moving. And so initially it has a V of 0. I wouldn't even have had to put that term in there at all if I didn't want to. But the red car has a mass of 6 kilograms, moving at 5 meters per second to the right. So we're going to let to the right be positive, like we often do, and kind of work from there. Now notice when we look at the information for after the collision, cart number 1, the red cart, is moving to the left. I have to take that into account when I set this up. That matters. The fact that it bounces backwards makes a difference in the momentum and in what's going to happen here. So as I fill in the other side of the equation, notice I'm using those two masses again because they're still part of the system, but I'm putting that 1 meter per second in as a negative value because the red cart ends up moving to the left. I only have one unknown then, this final velocity of the blue cart. That comes out to be a positive number when I go through my algebra. And so since it asked for velocity, and velocity is a vector, I would want to make sure I include a description. I would always state the value as a positive number and then indicate the direction by saying, in this case, left or right. Other problems might say things like east or west or north or south, and so you would follow the pattern of the problem. All right, so this problem includes something that's, again, kind of a key phrase to sort of think about. We have two cars traveling, and the faster silver car is going to kind of rear end the little red car. But notice the question says, what is the speed if they lock bumpers after the collision? Okay, so that means that if their bumpers lock together, that they are moving together after the collision. This is something called a completely inelastic collision. It refers to something where they stick, the objects stick together and then afterwards move together. We're going to start in the same way though, indicating that momentum is the key strategy. And again, why am I choosing that? It's because the problem is showing me two interacting objects, and it's all about speeds. Those are both indications that momentum is the right strategy. But again, the key thing is that the speed at the end is the same for both of the objects. So there's not really a V1 final and a V2 final. It's really that the whole mass together is moving at a single velocity V. That's what I'm trying to find. So that's the right-hand side, the after equation. The left-hand side, everything's moving to the right, and so I don't need to worry again about positive or negative signs. Just really need to organize the information, make sure I put the right value of speed with the right value of mass. Notice that both objects have momentum to start with. So the total momentum is found by adding those two amounts together. And then we would end up dividing by 2,000, which is what 800 plus 1,200 is altogether. And we get 20.2 meters per second. Notice again that I'm done at this point. The question asked for speed, not for velocity, so I don't need to indicate anything about direction. All right, last one. Again, I want to make sure we talk about why we're using this strategy. Here we have two people, two skaters, Ken and Barbie, and there's an interaction, okay? They are exerting forces on each other as they interact, and that is a sign of a collision. It's actually sort of like an anti-collision. It's pushing apart. But it's an interaction, and that's where the ideas of momentum are going to be very helpful. So I'm going to start with that same statement. Again, whichever way makes more sense to you. I like this top one because it's simpler to write, but some people really like to write it all out and see all those m times v's on their paper. You don't need to put both of these down. One or the other is plenty. Now, the key thing is that they start from rest. Not just one of the skaters, but both of the skaters start from rest. They're just standing on the ice. And so they both have an initial velocity of 0. There's no momentum to start with. Now you might say, if there's no momentum to start with, how can anything happen? Well, that push causes one of these momentum values to be positive and one of them to be negative. And that's really what happens there. So the overall net momentum is 0, even though each object has momentum in a different direction. Strange things about vectors. So I could put in, let's see, Barbie's mass was 54, and she ends with a velocity of 2.5 meters per second to the right. So I chose to put that number in as positive because I usually think about to the right as positive. And then when I solve this, you would end up saying this whole side was 0, and you would bring this number, this whatever this turns out to be, 54 times 2.5, you would bring that to the other side, it would become negative. So your answer would end up being negative. But again, that makes sense. If as a result of this push, Barbie moves to the right, I expect Ken to recoil to the left, okay, to react to that and move to the left. Equal and opposite forces producing equal and opposite motions in this case, since there was no motion to start with. And so again, it asks for velocity, so that's going to indicate I want to say something about the direction. So I could say here that Ken moves to the left because originally they told me Barbie was to the right. So that sort of gave us the way of describing the motion.